Today on Zeno Lidon, I'll be taking a look at a pair of LasNova 50s, which are relatively high quality DPSS lasers manufactured by Lasos and are designed to do about 100 milliwatts of 532 nanometers. Now, they no longer do this. Why? Because one is old, probably has a bad pump diode, and the other one was stabbed with a screwdriver during radical decommissioning, which is plenty of reason for my friend Kevin, who runs Starlight Photonics, to send these over to me to mess around with, and for you to enjoy watching. So we're going to get into it. The other thing that Kevin sent over for me to use is the original driver board that goes with these lasers. So this will hopefully help us get some information about what could possibly be wrong with these laser heads here. Now I have my laptop set up here and a couple of other things that I'll be connecting, so let me go over what's going on here. I've got the laptop to run the program. We'll be using Lasos Commander. I've got this power supply back here, which is a server power supply. It does 5 and 12 volts. That'll be running my little TEC cooler that the lasers will sit on. Got a 24 volt power supply here, which will be running the driver board for the lasers. I've got my serial cable adapter and so on and so forth. So, simple stuff. Anyway, I'm going to go over what I'm doing, so that way you know. Firstly, set the little cooler here. That's connected. Good. Let's see, which one should we take a look at first? The low power or the screwdriver one? Let's take a look at the screwdriver one first. These kind of come with a weird cable. Yeah. Kind of have to hang it over the end. We'll leave that connected like that. Plug that into the other end of the driver where the laser head connects. And then connect the 24 volt power. I'll find the pin out for this later on. Post that up. And then the serial to the driver. Okay. I think we're good. So what I'm going to do is I'm not going to power this actively right now. I want to get information just as it sets, and I don't want to have the cooling properties of this one active to play around with the readings that we get from the laser head. As I run the laser head more during this video, I may have this running, but we'll see if that's required. These are pretty small laser heads and should only produce about, what, maybe 5 watts of heat? Not all too much. Alright. Now that we have that running, let's go ahead and plug in a 24 volt power supply. And you'll get some lights up here. I'll turn off the light so you can see that. Little blinking light. Turn it on. I'm going to launch the Lasos Commander program. And once again, that talks through serial. Very simple program. Go ahead and zoom in on that so you can see what's going on a little bit more too. I'll raise the camera. Okay. Now these lasers do take a couple of minutes to warm up, but as they do, we can connect and we can watch the graphs. Go into expert view, we're going to check temperatures, and that's our graph right here, and we'll see how that changes over the course of 15 minutes per each laser. Get some information that way. This also does some other data logging as well. It does power, and in the case of it actually reaching the full output power, I believe you can also set the output power as needed, but these don't produce that much, so you really can't set it. Let's not point the laser at the screen directly. Grab that, that'll work. Alright, so there's our output right there. As you can see, we don't have any of this enabled in software yet. Take a look at the current. So here's where the pump diode turned on, and then we have what looks to be some sort of soft start after threshold that's raising the current. Laser set up, lasers on. Alright, the temperatures are one of the most important things to watch. So what I really want to do is I want to see if both TECs that are in the laser stabilize. We have one TEC that controls the pump diode temperature, which I believe is the white up here. So as more current is being pushed into it, we can see that warm up. And then we have another TEC, which actually warms the resonator for second harmonic generation, which converts to 1064 over to 532 nanometers. And that crystal in the resonator, which is probably KTP or lithium triborate, LBO, used as a second harmonic generation crystal. We'll take a look at the construction of that later on, but that's what this red line is here. That's the resonator temperature. So right now, I just want to see if these stabilize for both lasers. We'll come back in a couple of minutes with some information and graphs. Okay, it's been 15 minutes and we have some information on some graphs we can take a look at. So let's go ahead and do that. Bring this lower. Zoom in a little bit. Alright, so the white line that you see right here, that's the temperature for the pump diode. So it looks like at startup, it started pretty cool. Temperature went up a little bit, dipped, and it looks like around this point it tried to stabilize. And then we have what looks to be a thermal runaway on the pump diode. So I'm suspecting in this laser head there's damage to the thermoelectric cooler and it can't cool the pump diode properly. However, if we take a look at the red line down here, that's for the resonator, and that looks like it held perfectly. So that TEC should be just fine. And that makes a lot of sense given the type of damage that this laser has received. I'll go into that a little bit. Let's take a look at the power that we're getting out of here. And the current actual output power is 6 milliwatts. We can see that there's been a couple of high points and low points. So this is probably just where the pump diode has gone into like the 808 nanometer range, where it's a perfect absorption, and as the temperature drifted, it went in and out of that. So not very stable here. It looks like our high point actually is in the high 15 milliwatt range. So that's the current peak that we can get out of this laser. It looks to be about 15 milliwatts. Well, what else can we take a look at? Take a look at the current. Yep, that came up right away and held steady. So there's no problem with the current regulation. And it looks like it's holding at about 1.6 amps. So that's fine. Yeah, the only disturbing thing I really see out of all these graphs right now is that it looks like we have a broken thermoelectric cooler for the pump diode. Let's go into why I think that is. So this is the laser that was damaged by the screwdriver stabbing it during decommission. Disconnect this laser real quick and power it off. Wrong light. When you got to use the laser to plug in another light. There we go. Look at, you're still serving some use to man. Unplug the laser. All right, let's take a look at the actual laser head. See what the damage is. I'm going to pop off the cover. And you'll notice that we can see where the screwdriver tip actually hit this copper block. It looks like it got stopped rather abruptly. But between this copper block and the base of the laser, there's a thermoelectric cooler. So if you were to imagine a side impact hitting this copper block with significant force to actually dent the copper that badly, it probably cracked some of the junctions inside the thermoelectric cooler. Yeah, that's a little warm, but not too bad. So we're going to take a look at the TEC in this laser, probably replace it and see if that fixes this one. What's most impressive about this laser? Only 4 hours on the counter. In fact, maybe you saw it, but yeah, incredibly low hours. Who stabs a laser of this quality? 4 hours. 4 hours. That's it. This thing did its job for 4 hours, and then was brutally just decommissioned. That's okay. We have this laser right here. So we're going to do the same thing. I'm going to connect the laser up we're going to take a look at the information that is presented to us on the graphs at 15 minutes and see what we can learn from those. Put that there. Most good. Turn on the laser. All right. Connect laser. All right. Connect. Expert view. We can take a look at the temperature graph. You know, it's starting off almost identical as the other unit. So we'll see how this goes. Once again, I'll turn off the light so that way you can see the graphs a little bit better. Once again, the white is the pump diode temperature and the red is the resonator temperature. So I got that same little dip right here. So we'll see how that changes or not. Alright, it's been another 15 minutes. Let's take a look at the graphs in the program with this laser head. So these are two output temperatures. Once again, the white is the pump diode temperature and the red is the resonator temperature. And we can see that both of them have stabilized and we have a nice line over a long duration. So both of the thermoelectric coolers and the feedback for temperature control in this laser head is good. So let's take a look at power, see what we got. Power has actually been pretty consistent at about 1 milliwatt. So about 1/100th of the output power we should be getting, which is not great, but at least we're getting something. And that's at a current range of about 1.8 amps. So I'm suspecting that these lasers on the inside for the pump diode have a 2-watt, 108 nanometer C-mount, which is very common for lasers of these style and size. Yeah. So this one looks like it has a bad pump diode, or it's possibly out of alignment. The laser does have 3,100 hours on it, so as I said, much higher than 4. And so it's a little old, but hopefully we can fix it with alignment, or I have a pump diode that'll fit in there floating around. There is one more test that I want to do, and that is with active cooling on the other laser head. So I'm going to go ahead and set that up real quick. That'll be easy. I'm going to turn on the TEC. Okay, that's running. I'm going to disconnect this. And we're going to try to actively cool this and see if we can get more output power by cooling the pump diode. It's going to be a lot more cooling than the original pump diode in there. There's 240 millimeter TECs, so we'll consider that overkill. And hopefully we can get some better output power with the pump actively cooled. Of course, at peace we have no closed loop feedback, so we might get a nice peak of bright output power, but it probably won't be for long. Okay. Plug in the laser. Search laser. Connect. And we'll do the same test otherwise. So, expert view, temperatures, same as before. And now I'm going to set this thing to high cooling power. And then we'll do another 15-minute test to see if that improves the temperatures and the output. Okay, another 15 minutes has passed. Let's take a look at our graphs. So once again, we have the white line, which is our pump diode temperature, and the red line, which is our resonator temperature. And it seems like that during the active cooling process, the temperature went down, 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 and we have this low dip. And then it goes up and stabilizes. What I think happened is as the temperature dropped, the broken junction in the thermoelectric cooler made contact due to material contraction, And then the sensor and the laser said, oh, no, we're too cold. And it warmed up and stabilized. So it definitely does look like it's an intermittent connection in that thermoelectric cooler. Let's take a look at the output power, see if that was more stable. Well, it looks like we have a large peak jump right here. So that kind of tells me that, yes, if the pump diode was at the correct temperature, we probably get a lot more output power. That peak power was 16 milliwatts. Oh, hey, it's actually going up right now as the pump diode warms up. We'll let that warm up and see what the peak power we can get out of it is. In fact, you know what I'm going to do? I'm going to raise it off the TEC. Oh, man, we created a water out of thin air device. And then we'll let that pump diode warm up and we'll track the output power, see what our maximum is. Yeah, it looks like the peak power is going to be around 16 milliwatts. So I am betting that the temperature for the second harmonic generation is also out of tune. And that's okay, we can change that a little bit with hardware hacks, because I don't think the software supports any of that, which is going to make the whole video way more interesting. So yeah, looks like we have our information. Looks like this one needs a new TEC for the pump laser diode and some temperature tuning. It should have a really good pump diode in it, given that it only has 4 hours on it. And this one, hopefully it's just an alignment issue or it needs a new pump diode, but we'll know more once we get inside of the laser head. Here is the LasNova 50 that I believe has a damaged thermoelectric cooler for maintaining the temperature of the pump laser diode on the inside of this laser head. So I'm going to see if I can fix that. Now, getting these lasers open for the first time can be a little bit of a trick. There is only one screw here that needs to be undone, but the catch is this aluminum lid is also sealed onto the rest of the laser with this rubber material. So if I go ahead and slide this upwards, you can see some of the residue of that material here on the bottom of the laser. And this is kind of tricky to get into because these side walls here and here are raised to meet the height of the laser lid. So there's no way to really get a blade in underneath there from the two sides. And you have to work your way in from the bottom. So that can be a little bit of a trick, but it's not too hard. And once the lid is removed, we can see what's inside of the laser. Now there's this control board right here that sits on top of the laser assembly. And this control board is held on by 2 nylon screws. So one goes here, this one's already removed. And then there's these 2 screws here on the back. The PCB actually extends all the way to the back of the laser underneath this metal area. And this is what this LED is attached to. And this is what the pin header in the back also connects to. So in order to remove that, is one thing that also needs to be done besides removing all the screws. And that is to desolder all the wires that connect to the control board. So before I do that, I'm going to give you a good view on how these wires are normally connected. So that way, if you're working with one of these, you can follow along. All right. Now let's start removing some wires here. It's soldering time. Alright, that should be all the wires. So, grab some other tools here. Alright, now the whole control board on the inside should come off. I think this one's also glued on in the back. We'll give it a little bit of torque. Yep. And you can see the glue there that held that on. I missed a wire. Okay. Now, I'm not going to go over what all the wires and stuff do on this one. all I'm going to do is replace the TEC and go over the physical construction a little bit. We'll get into the high hours head in a little bit. Now, I am going to remove the entire laser assembly here, the optical assembly, off the TEC. I want you to know that right here, there are little glass blocks for spacing. So keep that in mind when you're clamping it back down to the base of the laser. And it should just be 2 screws. Alright, and then this whole assembly will lift up and out. So we're going to carefully do that. And then we have access to the thermoelectric cooler there underneath. Go ahead and fully remove those screws. And it looks like there's insulating plastic rings there too. Because if it's just a C-mount laser diode, they're usually case positive. So you don't want that case positive to go to ground. That would be a short. It looks like the TEC is glued on. Oh, thankfully it's not a stiff glue, so we should be able to break that off pretty easily with something. With what is the question? That'll do. Brand new. So I gotta break off the TEC wires that are glued here on the back. So let's do that without injuring ourselves. That'll work. And then here. Oh yeah, no. That TEC was definitely done. Thing just crumbled. Wow. Well, that confirmed a whole bunch of that. That got hit real hard. Wow. I've never seen a TEC that absolutely damaged. Like, I'm just lightly rubbing it. Are any of these still soldered on? Okay. Actually, we can kind of see where the force is. So, if it got hit, if these are missing and these aren't, sheared off this way. So that means our impact is, yeah, hold on. Our impact is here. So yeah, boom. That's exactly what happened. They all got torn off. Interesting. That's crazy. Strange TEC size too. It's like 20 by 25. Wow. That's incredible. Alright, well, we got half the TEC off. Still need to get the rest. Little tappy tap tap. Hopefully it'll debond easily. That is not debonding easily. Okay, I'm going to hit it with the heat gun a little bit, see if that helps. That's as warm as I want to get that pump out. Of course, hitting this is not exactly friendly easy. Yeah, friendly easy. Friendly either. I hate everything about this. I'm going to remove the pump diode and actually heat that up to an appropriate temperature, because I think that's the only thing that's gonna do for that. Pump diode is successfully removed. Boy, I'm going to remove the crystal. I did not want to take this apart this much to replace the TEC. No siree, Bob. Well, that's not what I expected. Alright, well, I grabbed this with an insulating object. That's still very hot. Right. Well, that's going to get interesting, isn't it? I need to grab the vise. Alright, now that I have this locked into the vise, hopefully I can give it a couple of decent good whacks and get everything off. The vise will help absorb some of the vibration from hitting it. But man, it's not exactly the way I want to do things. Well, this is getting complicated. See if I can take off the MCA. It's got to be like a little clip or something, yes. Oh, it slides. That's interesting. Okay. Removing that. That did not prove successful. Wow. More heat. I do not like how hot I'm going to have to get this. No more Mr. Nice Guy. No more Mr. Nice Guy. 4 hours on it. This laser had... Fuck. That's hot. 4 hours. This laser had 4 hours on it. 4. Well, you know, I don't even know what to say about that. I really don't know what to say about that. Like, in order to fix this laser, I need to remove the TEC. Like, that's not optional. Okay. Well, at least we have a good pump diode for the other one, if anything else. But, like, this is ridiculous. I've never seen a TEC like that. Is this all glued together too? Oh, it sure is. Well, that's nice. Oh. How? 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 So I have some good news and some bad news. The good news is I found a way to get the rest of the ceramic substrate off the copper. And that was by taking a metal pin like this and just hitting the top of it. And that broke up the ceramic and it came off pretty easily after that. Now the bad news. So, I was using one of these handy dandy tools to scrape away the little bits of copper and ceramic that are still on there. And well, you know where this is going. So I'm going to come back to this probably tomorrow after a little bit of healing and a band-aid. And you know what the ironic part of this whole thing is? So, some places when they decommission equipment, they will deliberately destroy it so that way people cannot injure themselves with it. You see this with like lasers that have cut wires and stuff like that. So, the ironic bit about this whole thing is that this laser was just deliberately destroyed after 4 hours of use so somebody couldn't hurt themselves with it. Well, that backfired. some progress has been made, and given how delicate these optics are, I'd like to go ahead and get this all put back together sooner than later. Let's start with discussing what this block is. So this is a copper block that the thermoelectric cooler was glued onto. I did my best to flatten this surface out and prepare it for a new thermoelectric cooler. And all in all, that actually turned out really well, given the situation. Let's take a look on the inside of the copper block, and you'll notice that there is a lens. So this is a condensing lens, and what this lens does is it takes the pump laser light from the pump laser diode, that's 808 nanometers, and it focuses it down to a point, and that point ends up going into a crystal. Now there's actually two portions of this crystal. It's either going to be a neodymium doped vanadate or a neodymium doped yttrium aluminum garnet. And what that would do is it takes the 808 nanometer laser light, converts it over to 1064 nanometers. And then there's another crystal that's either going to be potassium titanium phosphate or lithium triborate, and that'll be our frequency doubling crystal. Now unfortunately it's a little hard to see all the crystal layers on the inside. That's about the best view you're going to get. I wonder if this little spring plate will come off. See what you get underneath there. Yes? No? No, not really. Well, that's about the best view as you're going to get. I don't want to break this one. The crystal does sit on a thermoelectric cooler, and that's for controlling the temperature of the second harmonic generating. The KTP or LBO is really fickle to temperature, so that needs to be maintained at a exact constant set point. There's a thermistor right here. So this blue strip is actually the temperature sensor, and that is what gives the feedback to the controller to let it know what temperature it is. You'll notice that this copper block right here is actually glued to a thermoelectric cooler itself. So we take a look on the inside right here. This white material and on up is the thermoelectric cooler, and that is what controls the temperature of the crystal in the front. So what's really interesting about this is it looks like the crystals are actually spaced out with like a silicon like material. I've never seen that in a laser quite like that before, but yeah. Really interesting. Let's see what else we got going on. Okay, so orange wire, that goes up to the thermoelectric cooler. I'm going to have to replace that because the heat gun got it. And then here's the other thermoelectric cooler wire. So that's for the thermoelectric cooler on the inside. And then we have these two wires right here. Those go to the thermistor. I think that's it. Yep. That's about it for this block here. Now, in the back of the block is where the pump laser diode gets inserted. So let's take a look at the pump laser diode real quick. So there's a very common style of pump laser diode. This is what's called a C-mount package, and it's probably a 2 watt at 808 nanometers. And we can also see that there's a FAC lens installed. So FAC is for fast axis correction. And if you look very close, you'll see that there's this little cylinder on there that's glued to the front. Kind of hard to see. See if we can get a little closer here. Yeah, so there's this little glass cylinder, cylindrical lens on there. These are the gold bond wires that go over, and that is case positive, and this wire that comes off across the top. So right there, that's your negative. So positive, negative. I'm going to reinstall this back into the back of the resonator assembly, so that way it's protected. Let's see, and that goes in this way with the pump diode here tucked in this little cutout. So I believe it was vertical. Yes, it only goes in one way. Now, the positioning of the pump laser diode is, of course, fickle too, because that's part of the alignment optically. So we may have to move this pump diode around as the laser is running, at least for a little bit, just to make sure we have the most ideal alignment. We'll cross that bridge when we get there. Alright, and just to point out too, the pump diode has its own NTC thermistor as well, just like the crystal does for temperature monitoring, and that's this blue strip right here. Really interesting thermistors. I got the blue wire here, which is the laser cathode, and this yellow here, and that is just connected directly to the copper, because of course this is a case positive laser diode. So go ahead, tighten these down real quick. Alright, let's take a look at this portion here. So this is the front portion that goes on the resonator here. And I believe it goes, yeah, it goes this way because those wires stick up. Like that. Now, I don't think there's all too much going on. I think this is just the optical pickup. So let's go ahead and take the front off real quick, see what's inside. Strange. Yeah. It's a fleck of dust on there. I'm gonna have to clean that off. It's probably the infrared filter there. Good, it doesn't fall out. And then on the other side, quite possibly a lens too. Hard to tell. Looks like we're gonna have to open this up for reasons. Oh, these screws don't want to come out. Yeah, I wonder what that is. I don't see any optical sensor for feedback. Huh. Might be the back of the sensor. Very strange. And then this, if anything, it's a spatial filter. That is all it is. And that means that I'm going to have to line up the beam with that little dot. Lots of optical alignment is going to go into this. That's okay. We can only make it better, right? Now, there's a couple of things I do need to do. As mentioned earlier, I do need to find the sweet spot for the position of the pump laser diode. So I think my best bet on that one is going to be hooking up the pump laser diode to a constant current driver outside of the laser, and then seeing where the best position is for that manually before I put everything together. The other thing too that I'm going to need to do before I put this all back together is I need to modify the bottom bracket here. Let me explain to you why. So this is the size of the original thermoelectric cooler, and this is the size of the replacement. Now they're close, but you can see that this one's a little shorter in thickness this way. So I overlay it like like this, it is about 1.5 millimeters difference. And if we take a look at this little pocket here, you see how that fits in? And there's a little bit of wiggle room in here, but that little bit of room also accommodated the wires that went out of the back. Now, I have this as a 20 by 20 millimeter thermoelectric cooler, and this way, if I drop it in, it makes good contact, no problem, but I need to run the wires out of the back of the unit. So, I think what I'm going to do, I'm going to remove this. I'm going to do a little bit of machining and make 2 pockets here, so that way I can run the wires from this thermoelectric cooler the way I want to. So, go ahead and take that little bit out real quick so I can access it appropriately. There we go. Weird. Why would they make that piece? Very strange. Alright, I'm going to get through this. Before I start reassembling the laser, I want to make sure that the pump laser diode is in an optimal position to hit the crystal assembly correctly. So these 4 screws that hold the pump laser diode in the copper block here have a little bit of play, and that allows the pump to be adjusted left and right and up and down. Now, there's a condensing lens right about here in the module, and that means that I can adjust where it lands through the lens like this, and hopefully I'll be able to tune that so it's in a good spot. I have a laser driver set up right here, which will be constant current. I can adjust that with this potentiometer right here, and I'm going to use my main power supply at about 5 volts to run that. This laser diode is rated for at least 1.8 amps. I'm going to bring it up to 1.5 and see if I can get the crystal to give us a good output. Over here I have my multimeter, and I have it configured in series with the load and set into the position where we read the current in DC. So I'm going to slowly turn up the constant current driver that I have here until we hit that 1.5 mark, I would say. And we see a little bit of green laser light there. That's good. We'll start with that. And I'm going to carefully loosen the screws here in the back just a little bit. That way I can adjust the position of the pump diode. See where we get the brightest output. Move that around a little bit. Have to get a little wedge in there or something. That works. That might work. Alright, so you see how that instantly got brighter right there? Let me rock it a little bit more, see if we can see it dim out. So I'll move it back in that position. And that plays a significant role in how efficient this laser is. So I'm going to go ahead and turn off the light and see where our brightest spot is. So to be honest, I'm surprised this thing is still working given the abuse that I've already given it while getting that thermoelectric module off. So, loosen up the screws a little bit more, just for the time being. Let's see where the best position is. I'm making anti-progress. Alright, I'm going to tighten up the kitty corner screws here. And get something thinner that I can stick in there and kind of make adjustments. And that's without temperature control, and I'm not even maxing out on the current. That's only at 1.3-ish amps. Let's bring it up to 1.6, see how it handles. And then we'll get a lot brighter output when we have control over the pump diode and resonator temperatures. So, a little bit of an output difference, but not too much. Bring the power back down. Okay, that looks good. Shut that down. And now, I want to just make sure that the thermoelectric cooler for the resonator is still okay. So what I'm going to do is I'm going to do a continuity test on that, which is the white wire and orange wire up here. Oh, we don't need these anymore. And the continuity test will just tell me if that survived all the heat gunning and everything else. If it did, I think we're going to be a go to reassemble this laser. Yep, that looks fine. So, despite all the heat gunning, it looks like that part survived really nicely. Let's put this laser back together now. So I have the entire optical assembly right here, and I have the laser base and chassis here. This is the new thermoelectric cooler that I'm going to use. It's a 20 by 20 millimeter TEC, and I have made these little pockets here in the copper piece, so that way the TEC fits in as it should. So, like that. And then I went to go and check the distance by putting it all together. And what do you know? The TEC was not thick enough, so I had to make a little aluminum spacer that will sit on top of the TEC like this, and then give me the correct height, just like that. So let's go ahead, get the thermal compound out, start putting this all together. A little bit of thermal paste here on the bottom. Should smush out nice, fine. Drop the TEC in. Okay, put some thermal paste on that now. That on there, just like this. And then some thermal paste on that. Now we prepare the laser module itself. Make sure that none of the wires are being clipped and that it sits properly. Okay, that feels pretty good. The electrical inserts, because this is, remember, case positive, and you don't want to have that positive leaking out, touching ground, causing a short. And now I'm not going to tighten this all the way down. I'm going to tighten it most of the way. I want to see what that fit is, because I got those glass inserts that should sit in here. Yeah, okay. So, I'm going to go ahead and put those inserts in. And this will set the exact height of the entire optical assembly, and the thermal paste will fill in the slight difference. You know what? I'm going to use a little bit more thermal compound on the interface between the aluminum and the copper there. And I want to make sure that that is as aligned as it can be. Go ahead and carefully screw these screws down. Now remember, you're clamping onto the 4 pieces of glass, 2 per side, and a delicate TEC. So if you hear cracking, you've gone too far. Alright, now it's time to, say, fix this wire that comes off of the positive side of the TEC for the resonator. Alright, I am going to go and resolder this board back on. We'll fire up the laser, test it out, see if it works any better. So I took a few hours and I played around with the optical alignment of this LasNova 50 head that I just got done installing a new thermoelectric cooler in for that pump laser diode. And I think I have it reasonably well aligned at this point. So let's go ahead and do another test run on it of 15 minutes and see what happens on those graphs. Now there's going to be 2 graphs that I'm going to pay attention to. First of all, I'm going to pay attention to the thermal graphs for the resonator and more importantly the pump laser diode, just to make sure that those are working. And then we'll go ahead and take a look at the output power graph to see where that lands us once everything hopefully reaches a good thermal equilibrium. So let's go ahead and do that. Plug in the laser. Connect laser. And now let's go ahead and see what these graphs say. So, temperatures. So once again, the red is for the resonator crystal assembly in the front there. And then the white is going to be for the pump laser diode temperature. And what we're looking for on this graph is for the lines to have a point of equilibrium. And that'll be represented by them being completely horizontal without any vertical change for a good duration of time, indicating that that set point for the temperatures has been reached. After we reach that set point temperature, we'll take a look at the power graph and see what that looks like. Go ahead and zoom in a little bit. That way you can see those graphs a little clearer. We'll have the laser output here on this piece of paper. Alright, and that's 15 minutes. Let's take a look at our graphs. So we take a look at both the red and the white line on this graph. We can see that there is a long duration where the line is perfectly horizontal and doesn't change vertical at all. So that means that the TECs and the feedback for both the resonator and the pump laser diode are working perfectly. So that new TEC definitely doing its job. It also looks pretty stable too. Let's see how stable though. Go over to power, and we're currently producing 4.6 milliwatts, which is, well, a very long way from 100 milliwatts, and in fact that's even lower than what I started off with, which was I think like 19-ish milliwatts. So we have a 75% reduction of beam power, but given the fact that it's taking a lot of heat gun abuse getting that TEC off the copper, that's understandable. But what's interesting is that right here in the beginning, we have a hot peak of a higher output power, which looks to be about 11 milliwatts, which indicates that the temperature is set incorrectly for either the resonator or the pumped laser diode. So if we can change those temperatures, we can hopefully find that high peak and get more performance out. Let's take a look at the program real quick. If there's going to be any kind of settings, it's probably going to be in laser setup. So let's see if there's any kind of temperature adjustment. There isn't. Okay, well, that just means we're going to have to tackle this from the hardware side of things, which is completely doable. It's time to hack a laser. So at this point, what I want to do is change the temperature that the resonator and pump laser diode run at. And they have specific temperature ranges for a reason. So the pump laser diode should be set to run at 808 nanometers, which is a peak absorption line for the neodymium ion that is inside of our 4-level gain medium. And then that, of course, produces our 1064 nanometer laser light. And the second harmonic generation crystal, probably KTP, potassium titanium phosphate, also has a temperature of which it'll convert that into green most effectively. Now, since I can't modify those temperature ranges in software, I have to do it on the hardware level, which is pretty easy once you understand how these temperature sensors work. While many lasers have usually a 10 kilo ohm NTC thermistor, these actually have a 1 kilo ohm PTC thermistor. And the difference between NTC and PTC is that PTC gets more resistive as it warms up, where NTC gets less resistive as it warms up. So, at about 25 degrees C or 70 degrees Fahrenheit, we should see about 1 kilo ohm. Now, this is a very warm shop, and that means that I expect to see a higher value on those than 1K. I'm going to go ahead and remove our two sensor wires here. There's actually 4, but we got these 2 white ones right here, and those are common. And then the blue is for the resonator, and the black is for the pump laser diode. So, I'm going to go ahead and pull off the other end of the sensor for the resonator real quick. Just like that. And then we can verify the resistance. Now, as I said, it's gonna be a little higher than 1K because it's warmer in here. It's like 93 degrees. Yep, it's 1126. And if we reintroduce our old friend, the heat gun, and warm up the laser, the one task that I do not want to do in a 93 degree shop. We'll warm that up a little bit for demonstration scientific purposes. And you can do this to confirm whether you have NTC or PTC. Once again, if it's NTC, the resistance will drop. And if it's PTC, the resistor will raise. Alright. That should be a little bit of additional heat. We don't need that much. Go ahead and see where we're at. And you can see that it raised about 25 ohms. So, those are our sensor wires. And what we're going to do is we're going to modify the resistance that the driver picks up from those sensors. So how are we going to do that? Let's bring out the drawing pad and I'll show you. Alright, markers. So say we have our PTC thermistor here, which are these 2 wires here, and between these 2, draw an arrow, we have 1K. So we can modify that in 2 different ways. We can either put something in series with it, which will raise the resistor, and we don't want to raise it much. So if we remove one of these connections, let's see, go ahead, we'll say this one is a common between those 2, and we have removed this. So what can we do? Say we want to increase the resistance that reports back to the driver. Okay, we're going to put a potentiometer that we can change between the other end of the driver here. Say, that'll be what we read. So let's put a little resistor here. Yeah. Well, like this. There we go. There's a potentiometer now. But you only need to use 2 of the legs. You don't need to connect it up this way. But the goal is to have the sweeper set to 0, and then you're going to raise the resistance up. So we'll put this here, and we don't want to raise the resistance up too much since it's a very sensitive temperature. So we want to start at as close to 0 ohms as we can and go upwards like this. And say you're going to use a potentiometer then that's like 200 to 500 ohms. You want to keep that small. Now say you want to decrease the resistance that is being reported to the driver. Go ahead and draw those wires back. And in this case, the PTC thermistor is still connected to the driver. So we want to once again make as small of a change as we can to see where that perfect temperature range is. So we're going to take another variable resistor, potentiometer, and we're going to put it in parallel with the circuit here. But we want to start with a high value, unlike starting with a low value. So between these 2 points, we'll do this. There you go. It's a potentiometer. The sweeper we want to have set so it's all the way open, and then we want to decrease the resistance as we're doing our change. So because we want to make small changes, we're going to start with a potentiometer that's like 100 kilo ohms or 50 kilo ohms, because if we put something here that's like 5 kilo ohms, that's going to be a significant change in resistance already. That'd be 5K on top of 1K, where if we have 100K in parallel with 1K, that won't be as significant of a change. So I have my 2 potentiometers here. I have this one, which is my 50 kilo ohm, and I have this one, which is my 500 ohm. And once again, you only need to actually connect 2 of the wires up. I have them configured like this. I have the 500 kilo ohm configured, where counterclockwise is the closest to 0 ohms, and clockwise is the closest to 500 ohms. So that way, counterclockwise is my as close to factory as possible set point. On the 50K, I have it set so counterclockwise is 50K with this 5K resistor in series, so that way I don't completely short out the board, which gives me a total of like 60 kilo ohms with that resistor. And if I turn clockwise, this will get less resistive or more conductive, meaning I'll decrease the value that's reporting back to the laser driver. So let's go ahead and see what we get with the 500 ohm potentiometer. And once again, that's going to go in series. So I'm going to take these 2 wires here, and I'm going to solder one onto the board, just like this. And then I'm going to carefully solder the other side up to the PTC thermistor wire. Just like that. And then between those 2, I can verify that I'm starting as close to 0 ohms as possible, simply by testing across this right here and this right here. So I'll be adding 1 ohm total resistance about, which shouldn't be much change at all. And then the way that I have this configured, once again, turning this clockwise will increase the amount of resistance that's read by the laser driver. And of course, there is some room for compensation. The laser driver itself will be looking for a particular temperature set point. We're just altering the the PTC thermistor to send back a false signal. That's okay. We don't care about the actual temperature range as long as it's ideal to get us as much laser light as possible. This is a laser driver, not a thermometer. And that is a broken wire. Radio. Go ahead and fix that real quick and we'll turn on the program. Now, of course, we might be going the wrong way, which is why we can add and remove resistance with this pair of potentiometers. So we have a 50-50 chance at getting some improvement. So hopefully luck is on our side. Let's go ahead and reset the camera so you can watch what happens on the screen. Anyway, yeah, let's see how this does. I'm going to turn off the light real quick so we can see those graphs, and we'll wait till this laser turns on. I'm going to take my turn pot tool and I am going to turn clockwise that 500 ohm potentiometer ever so slightly. Remember, we're making very small changes to the temperature, and you should see that change in reading reflected with the red line, which is the resonator temperature. So let's go ahead and turn that potentiometer a little bit. Well, I was wrong. That was the laser diode temperature. Gonna swap those wires around. Hey, but we can see changing the temperature of the laser diode does in fact have a significant change on the output. That's good. But the most important one is the resonator. So let me go ahead and switch those wires around. So I'm going to do exactly what I did before with just increasing the resistance on that thermistor, except it'll be the resonator like I planned it to be this time. So now we should see that change on the red line. So I'm turning up the 500 ohm potentiometer. We see that the red line has increased a little bit. And we'll see that restabilize. So that's kind of what's going to be happening for the next couple of minutes. And if I bring it down back to that 1 ohm position, that red line will drop and then restabilize. Now, the controller wants to stabilize it at a certain temperature. So every time we reach a set point and it stabilizes on the program, it'll show the same temperature. But what we're getting in the program is not accurate. Remember, we're modifying the resistance of that temperature. So that's not important. What's important is to see where our peaks in power are. Now, once again, at this point, we're getting 2.9 milliwatts, and let's see, it went up to about 12. So let's see if we can get to 12 or better. If we can't, then we want to try with the 50K potentiometer in parallel. So I'm going to slowly turn this up, and over the course of a couple of minutes, we're going to watch the power graph. Well, that's interesting. I thought it would stabilize to a set temperature that was identical to what it should be thinking it should set at, and no, it just decided it was just going to stabilize up here, it seems like. Either way, we have gotten no performance boost, so time to swap to using that 50K in parallel. So go ahead, turn that down, because we're going to be using that on the pump laser diode. Probably see that plummet on the graph real quick. Yep, sure can. Okay. Alright. This is a simple swap. Soldering iron on, laser off, program yelling. Here we go. I'm going to remove the wires that are attached to the 500 ohm potentiometer. And I'm going to reattach the wire onto the driver. Because remember, this time we're running it in parallel. And I'm going to start with the resistor at 60K and bring down the resistance as we go. And hopefully we'll see some improvement. Search laser. Next laser. Once again, we'll wait for the laser to reach that stabilization point. Well, the laser looks confused, so I think I'm going to swap that 5K resistor out for, say, a 20 or 47K. Hopefully that gets us somewhere, because this ain't working. Once again, I have some good news and I have some bad news. But before I get into that, I'm going to go over what I've done with my setup. So I have a 1 ohm resistor here that's in series with the PTC thermistor that's monitoring the resonator temperature. And on the pads that are connected to the controller inside of the laser head, I have a 1 mega ohm potentiometer that is in parallel with the resistor and the PTC thermistor. The good news is I have about 20 milliwatts being produced by this laser. So we're back up to the peak output power we were getting before. But I have seen this thing go up to 30 milliwatts. However, keeping it at 30 milliwatts has become a rather difficult task. And there's more bad news to come, I assure you. So let's take a look at our output power with the lights turned off, and it looks pretty good. It's not the 100 milliwatts I'd like to see, but it's a nice, clean beam, spectacularly good as far as beam characteristics. So if I can save this laser, that'd be awesome. I'm going to try to carefully tune the resonator temperature and see if I can get it above that 19.7 milliwatts that we're getting out now, and we'll see the output either increase or decrease once again on the paper. So I'm going to carefully turn the 1 meg potentiometer, and I'll zoom in so you can see the program here. We're going to be reading the output power. Move the camera up. By the way, that's in the camera. Alright, let's see if we can get better output. Let the frustration begin. And you want to make very small adjustments. See, as I said, about 20 milliwatts, easy to get, and it's pretty stable. But when I do a full sweep through the output, we get a really nice 31 milliwatts. And this laser makes me feel like an invalid, but let's go ahead and see if we can do another sweep, see if we can get that 30 milliwatts. But unfortunately, it might be a case that the crystal is just damaged, and it does that for only a second, or some other anomaly is going on, but that's very strange. Yeah, when I sweep through the temperatures, I get that 30 milliwatts. Alright, so back up to 22 milliwatts really quickly. So finding that stable 22 milliwatts is pretty easy. But look, none of this actually matters. Here's why. I'm not touching the laser. We're just gonna let it run. So I want you to notice on the program that we have no problem maintaining pump diode temperature or resonator temperature, and yet the laser refuses to start because it's looking for some weird characteristic curve in the way that the PTC thermistors read. And I actually have to sit down and mess around with the thermistor, sorry, not the thermistor, the potentiometer, in order for it to actually start the laser. Go ahead and do that. There we go. Yeah, the fact that I have to fiddle around with that potentiometer to get the laser to even start makes this whole modification, trying to hack this laser with the original driver, a whole non-starter. Since trying to modify the resistance of the thermistors inside the laser head did not go as I'd hoped it would, and of course I have to return this driver back to its original owner, I'd say it's time to get into the meat and potatoes of the electronics and get a little bit of an idea of what we need to drive these laser heads without use of the OEM driver. But let's take a look at that driver before we start doing that. No, I'll tell you right now, I'm not going to discuss stuff in this section right here because that is pretty much all digital stuff, like the timing crystal, Atmel processor, whatever this is, some analog to digital converters, and so on and so forth. I handle analog electronics and power electronics, so I'm going to go ahead kind of tackle how this board works from that viewpoint. So we got the 24 volt power that comes in here, and there's a couple of different components in this section for kind of protection and filtering. We got a fuse here, it looks like, a reverse protection diode here, and then this high frequency filter. From there, we have these 4 capacitors, some MOSFETs, 2 inductors, some capacitors and resistors, and some more capacitors here. We can actually take a look at everything from these capacitors all the way this way to these 4 capacitors as 2 things. And that is DC to DC step-down converters, which are called buck converters. So what happens is these capacitors get charged up with 24 volts, and then they get switched by these MOSFETs. Now, since we have 2 DC to DC converters, we have 2 sets of MOSFETs. So if you take a look, this MOSFET and this MOSFET are identical, and this MOSFET and this MOSFET are identical. And then we have one MOSFET that will send a pulse of current, electricity, into the inductors, and the other one, which is our rectifying MOSFET. So instead of using something like a Schottky diode, they use a MOSFET because the resistance is far lower. You don't have that voltage drop and less heat is generated. They're far more efficient. And these are called synchronous DC to DC converters when you have 2 MOSFETs instead of 1 MOSFET and 1 diode. On this side, we have our low side capacitors. So what ends up happening is one MOSFET will turn on for a moment of time, will cause a magnetic field to be formed in the inductor, and then when that magnetic field collapses, when the electricity current is turned off, then the other MOSFET actually ends up rectifying that, that voltage that comes off the inductor, and that voltage is then stored in these capacitors here. We have this capacitor, probably just for snubbing high frequency noise, and we have these 2 resistors here. So these resistors are actually for monitoring the current that is flowing through this DC to DC converter, just for protection and or whatnot. We got these 2 inductor looking things here. Those are probably for high frequency filtering given the application. After those inductors, we have some more capacitors here, and on the other side we have 4 more capacitors. I'll talk about those and about this section of the board a little bit. I'm going to go over these 3 components here, and those are all NPN transistors. We take a look at these 2 components here. Those are low resistance resistors. These are also low resistance resistors too. And these are current shunts as well. So what happens is as current flows through these, there will be a voltage difference on the 2 ends of the resistors. And that voltage difference can be compared to a voltage reference somewhere in the circuit. I'll talk about that more later on in the video. But essentially we have 3 constant current drivers. So this is one constant current driver right here, and that is being monitored with these current shunt resistors, and I'm betting that that is for the output current for the laser diode. Now, these two resistors are not tied together in parallel. In parallel. Instead, they're independent of one another. On this side, it looks like. And we have two different circuits that are constant current controlled. Now, these two transistors are connected to these larger DC-DC converters over here. And that is because I believe that they're used for driving the TECs inside of the laser head. And I'll tell you why I think that. So, the one clue that really does give it away, and I mentioned this earlier in the video when I was hooking up the new TEC inside of the laser head, I said, they have full H-bridge drivers. And an H-bridge driver is usually 2 N-channel and 2 P-channel or 4 N-channel MOSFETs. And if we take a look at these SOT8 components here, we have 8 pins, and I believe that these are dual MOSFET packages. I'm almost entirely sure that that's what they are based on their configuration. Probably an N-channel and P-channel combination. They could be 2 N-channels in each pack, which means we have 4 MOSFETs here. And 4 MOSFETs are needed to change the connection as far as the polarity on a circuit. So it's kind of like this. Figure that each finger is a MOSFET. And if I turn these 2 MOSFETs on, the power is going one way. Say if this is my positive, this is my negative. And if I turn these 2 MOSFETs on, well, now the connections are backwards. So if the TEC needs to cool, it'll connect it like this. And if it needs to warm up the laser, it'll connect it like that. But that's why there's 4 MOSFETs. So we have these 4 MOSFETs connected to one transistor. Of course, that's constant current monitored. That's important. I'll talk about that in a minute. And then we have the other transistor connected to these 4 MOSFETs right here. So we have 2 H-bridge drivers. That's because we have 2 thermoelectric coolers inside of the laser head. And they need to be current controlled because if you feed a lot of current to those TECs, they'll get hot or cold really quick, and you'll have these thermal oscillations. And I'll talk more about that later on in the video. But that's why you'd want to constant current control and also polarity control those thermoelectric coolers. Hey, for example, if you're running the laser in a very cold climate and you need to warm it, you need more current to provide that power to the TECs, and you need to be able to control the polarity. Say if you're running in a hot climate, well, you don't need to warm up that part, you need to cool it. So you flip the polarity using the H-bridge, these 2 MOSFETs here, and now you get that effect. A couple of other things to note. We have a DC to DC converter here and a DC to DC converter here. I think this is probably going to be for powering the pump laser diode inside of the laser head, so I'm not sure. And I'm not sure what this one's doing here, but since this is a pretty small one, that could also be part of the voltage rails for driving the digital stuff. Now it looks like we got some DACs and stuff down here. That's probably going to connect to the thermistors and photosensor inside of the laser head and translate those analog signals into digital ones for the smart bit. And it's funny, you got all this stuff going on. You monitor the temperatures, monitor the output power, and so on and so forth. You think a driver this complicated could auto-tune the most efficient temperature range and so on and so forth for the best output. But apparently that's just not the case with these drivers, which is a shame. So, yeah, that's pretty much how the OEM driver works in a nutshell. Let's go ahead and take a look at the electronics inside of one of the laser heads and see what modifications we may and or may not need to make to get this running with some very crude analog electronics. For this portion of the video, I'm going to go ahead and open up the low power laser head, and my goal is to figure out more of the pinout on the back of the laser and see what connects to what and if there's any modifications as far as the wiring to that pin header that is going to be required for connecting it up to my own analog laser driving hardware. So let's start by opening up the laser. Now, I'm not going to go into detail about the board. There's a microcontroller on the bottom. We can take a look at that in a little bit more detail. But quite honestly, I'm only concerned with a few things. And that is the connections for the pump laser diode, the 2 TECs, and then the thermistors. So, how I'm going to do that is to do a diode check. Now, you can also use continuity as well. I've got my multimeter and it's already set into diode check. And how a diode check works is it'll usually beep, and it'll have a sustained beep if there is next to 0 voltage difference between the two probes. So if it shorts out, we hear that. We know that there's a good chance that that is our connection. We can go ahead and verify that with the resistance to continuity, just to make sure that it's not going through something weird. But diode check is a good way to start off. So let's start with the laser anode and cathode, and those are the blue and yellow wires on these lasers. So the blue wire is the anode, positive, and the yellow is the cathode, the negative. Kind of confusing, but that's what they chose. So let's go ahead and see if we can find those connections. So I'm going to put the negative side of the probe on the cathode, and then this is my anode here. Diode check will apply a very low current to the circuit. So in most cases, you don't have to worry about damaging anything by injecting that voltage from your probes. So let's go ahead and see what we can find. And of course, I have two the pins. There's a key here, the missing pin, and that is referenced by this circle here. So if you have one of these laser heads, you can kind of follow along. So let's start off, right? Laser diode cathode. See if you can find it. Alright, looks like that. So, let's see, double check again. Third pin, right? Third pin. Okay, so we'll put that down. P, D, K. K is for cathode because C was used for capacitors. Of course, back then they were condensers, right? Alright, laser diode anode. Let's see if we can find that. Which is the blue. So same thing, just kind of go through. Alright, so third pin on the opposite side. Oh, B, T, A. A is for anode. Double check that just to make sure. Yep, okay, cool. Alright, so it looks like we can just apply current from a laser driver to those two pins. Now, one thing I did note when looking these lasers over is it seems like there is a transistor right underneath the resonator block. And what's odd about that transistor looking thing is that the pump laser output is reflected right down on the surface of that. Looks to be a transistor to me. And what's interesting is, if we follow those connections, we have a yellow here, we have the orange wire here that connects over to here. So if I connect that to here, I believe it's connected to one of the pins as well. We'll just run through real quick. Yep, okay, so that has a connection there. And this blue wire that I believe would be a drain or emitter from that transistor suspiciously connects to the negative, the cathode of the pump laser diode. So this thing could actually have the current regulating transistor already in the base of the laser. But yeah, so it's kind of interesting. I don't know what the cathode here is referenced for. Maybe it's for detecting voltage, who knows. But let's go ahead and try to feed some current into it later on anyway. The next thing that I need to find is the connections for the two thermoelectric coolers. So I'm going to go ahead and do that real quick, and I'll label those on here. But it's the same procedure. I'm just looking for that that beep. Okay, at this point I've determined some connections. So we have the thermistor common, which is the two white wires that are over here. So that will be the common ground for the two thermistors when I go ahead and connect those up to my drivers. Downside is that there's no direct connection to the other side of the thermistors. They're probably handled by an onboard analog to digital controller that communicates directly with the little microprocessor on the other side of the board. So it looks like I'm going to have to run extension wires from these 2 points up to what hopefully is an unused pin on this pin header, which leads me to the next part, is removing that board, or at least partially on one side, so I can flip it up and investigate the pins. Alright, let's take a look at the bottom of this laser. And there's a bunch of things going on. It looks like there is another current shunt resistor right there. You got another Atmel processor, so that's the MCU. And a couple of analog to digital converters, stuff like that. So that's probably one right there. So my goal at this point really is to remove this black rubber material, get a good view of what wires are coming from each pin, and see if I can find an unused pin. Actually, I need 2 unused pins, so that's the goal. So after I hopefully find those 2 pins, I'll come back and I'll do that wire extension and connect those thermistors up so we have access to them. At this point, I believe that I've finished making all the modifications to that internal control board that I need to in order for me to use my own analog laser hardware. Or at least that's the intent. But before I get into that, I just want to go over the absolute mental brain loop that I've had to deal with for the last hour, and it still baffles me. So, earlier in the video, I pointed out that there was a semiconductor component that was attached to the base of the laser. So I looked up the part number, and that is an N-channel MOSFET. And it has 3 wires attached to it. It has this blue wire right here, and that's the source. This yellow wire right here, that's the gate. And this orange wire right here, which is the drain. Now, you know how you see things in a certain context for long enough, and that's how your brain automatically sees them? It's kind of like asking you, how many wheels do you need to drive your car? What if you said 4, you forgot about the steering wheel? And that's kind of where I went with this. So I saw that we had a low value resistor that is connected to the source of the MOSFET, and my brain instantly said, well, that must be some sort of constant current regulating circuit in there. But then I got a little confused. So the source of the MOSFET was connected to the laser diode cathode, and normally it's the drain that gets connected to the cathode because you're regulating the current by varying the resistance of that MOSFET. And I did some more probing around, and then I found that the drain was connected to the anode of the laser diode on the inside. So I was a little confused, and I found that this was a whole circuit in series with the resistor and the MOSFET. And I was trying to figure out what was going on. But I think what they're doing is they're using that MOSFET as an active clamping component. So in some lasers, they have a relay or something of that similar nature that will go across the laser diode, and it'll act like a short to make sure that there's no damage due to things like ESD or overcurrent when you're handling the laser head, especially when it's disconnected like this. So that's what I think that they're doing, is they're using that MOSFET to close and become conductive, and then they dissipate some of that electricity through this low value resistor. And that kind of gets confusing in my opinion, because the MOSFET is going to become more conductive than the resistor, which means that a lot of the heat that's generated is probably going to get generated by that resistor there. So it would have probably been a little smarter to have a smaller SMD MOSFET with a really low on resistance on the circuit board, and then have your relatively low value resistor connected to the base of the laser. That way the heat that is generated doesn't go into the board, cause any kind of problems with overheating or warping or anything like that. Now, the other thing that kind of threw me through a loop is, sure, you can use a MOSFET for clamping, but I think they chose the wrong one for the application. So the MOSFETs can come in a couple of different types. Most people know N channel and P channel for regulating power on the positive or negative rail. But they also come in what's called depletion mode and enhanced mode. So depletion mode MOSFETs, if I remember correctly, they need a negative signal to become conductive if they're an NPN. So if you want to turn on a negative rail, you send a negative signal to the MOSFET and it turns it on, makes it conductive. And then you have something called an enhanced mode MOSFET, which is the much more common MOSFET, and you need a positive to turn on an enhanced mode MOSFET. And that is what they used on the inside of this laser for clamping. The problem is that an enhanced mode MOSFET needs a positive signal. So if the control board doesn't have any active current going to it to turn on the MOSFET with a positive signal, it's not actively clamping, which means it offers no protection as far as ESD. But if they used an N-channel depletion mode MOSFET, it would have worked a lot better, because they could have had a resistor to pull it down, and that would keep it actively clamped, I believe, even if the electrical signal power was removed from this board. So yeah, that took me a little bit of time to figure out, because I've never seen anyone use a MOSFET for protecting the laser diode like that. It's a little bit weird, and I don't agree with it. But anyway, the modifications. Okay, so very simple. All I needed to do was just use 2 pins. Now all the pins are actually actively used, but since I don't need any of the digital stuff, I just decided to use one of those wires. Focus, there you go. And I found that these 2 wires were close to one another and had a bit of access to the trace. So if I needed to rejoin the trace, that would be really easy to do. Plus, it's easy to keep track of where those wires are, because it's these 2 center ones right here. So that's easy for me just to remember. Now I'm going to go ahead, I'm going to reassemble this laser head. And then I am going to start with connecting up my own analog laser hardware. I guess I can do this all off camera, and we'll come back when I have all my stuff set up for that. Alright, I have the controller board mounted back in the laser head, and I have a modified wiring diagram for those pins in the back. One thing to note, I did flip the pins upper and lower to more accurately represent looking at the pins from this direction. You can see that this key has been moved down, and that gives us access to everything, hopefully, that I need. So, start with the pump laser diode anode right here, which is these 2 pins. These 2 pins are the pump laser diode cathode. We have connection to the 2 TECs, so this one right here and this one right here is for the resonator or crystal. You'll see that that's marked with XTAL, and X stands for Christ, and TAL is tau, so Christ tau. And then TEC is for, well, thermoelectric cooler. And then from here and here, we have the pump laser diode TEC connections. Now, because of the modifications, not only do we have the original thermistor common, but now we have 2 pins that are on each one of those thermistors. So here's the one for the crystal, the resonator, and then this one is for the pump laser diode. Sadly, the one for the pump laser diode was originally the LED negative for the indicating LED in the back, but since it's going to be used in my house and whatnot, the CDRH and FDA doesn't know that that LED doesn't work. It's my problem now. So I want to get into talking about the circuits that I use for actually running lasers. And here's the laser driving circuit. Now I want to go through exactly how this works, so that way if you're making your own laser driver, you'll have an easier time of doing it, since it's a very simple driver. It's based off the operational amplifier that is an LM358, pretty common part. And I'm pretty sure you could use a lot of amplifiers, but this is the one that I chose. And I want to point out the 2 main sections of the circuit. So first of all, I want to point out the voltage reference, and I talked about this earlier in the video. Now the voltage reference is formed by this TL431 and this resistor right here. So let's take a look at the connections on the ground. So here's our negative input or ground, a 0 voltage rail, and that gets directly connected to the 2 outer legs of the TL431. On the other side of the TL431, we follow this blue connection here. We can see that there is a resistor anywhere from 1 to 10 kiloohms, and that's directly connected to positive. And that creates a low voltage right here in reference to ground, or 0 volts. So this side is 0 volts, and I believe the TL431 does 0.125 volts in this configuration. That's just off memory. I might be wrong on that, but the important thing to remember is here we have 0 volts, and here we have an incredibly low voltage. As I said, I think it's 0.25. And we can select anywhere between that voltage here and 0 volts using the potentiometer is a voltage divider that we can select using the middle pin, which is the sweeper. So if we turn the potentiometer more towards the 0 of the voltage, it'll have little voltage. And if we turn it up more this way, of course, we'll be closer to that peak positive side. And we can choose anywhere between those two ranges. The sweeper goes out and connects to this pin on the LM358, and that is what allows us to have a stable voltage reference and select what voltage we get off that voltage reference. Now let's take a look at the other side of the circuit that controls the transistor here. So once again, we're going to start off with the 0 volt negative side, or ground, and we can see that there is a resistor here that I labeled shunt. So on this side of the resistor, we're going to have 0 volts. And on this side, we're going to have a small voltage because there's going to be a current that goes through here and out through the transistor and off to the laser diode cathode. So now we have two different voltages that are slightly positive. We have that stable voltage from the TL431 divider reference, and then we have a voltage that's generated by the current that goes through the shunt resistor. So what this circuit does is it provides an output that's positive from this pin right here that goes up through here, around through this current limiting resistor here, and over to either the base or the gate of our final transistor for doing the current control of that laser diode. And it'll only put out enough positive signal from the LM358 to turn on the MOSFET or transistor enough to reach the voltage here and match what's coming off the divider. So for lower current, if you move this towards a lower voltage on the divider, it'll only drive the transistor enough for enough current to meet that voltage on the other side of the resistor, and that's it. So that's how it limits current. It won't go above that set voltage. It's a really simple driving circuit. If you're going to make one of these too, I suggest that you put a capacitor between your 0 volt or your negative input and your positive, just to make sure that whatever you get off your power supply has a nice clean voltage to it. There's no ripple or whatnot on it. It helps with stability. So let's take a look at that circuit now in practice, and this is the exact same driver that I used before. Now I have two transistors that are in parallel. However, this circuit can easily get away with one transistor. These are the D822. You can pretty much use whatever NPN transistor or MOSFET you want. These two resistors right here are just additional current limiting resistors to the bases of these two transistors. It helps balance out the signal between them too, but you don't necessarily need to, especially with these lasers. Right here, that's that 10 ohm resistor that's on the circuit diagram. This right here is a 10K resistor, and that's also on the circuit diagram here. So all that does right here, all that does is if there's no signal coming from the operational amplifier, it just ensures that there's no positive reference on the gate, and it makes sure that the MOSFET or transistor is indeed in the off state. We got that this resistor here. Oh no, wait, this is a 10 ohm resistor. This is all for balancing. Yep, 10K pull down. Here's the shunt resistor. I have another one on the other side of the board. Here's the LM358, the potentiometer, a TL431. Everything over here you can ignore because that's just experimental modulation for this laser driver, and it does work very well. Oh, very simple board to make. Here's the other side of the board. So once again, if you're making one of these yourself, you just go ahead and continue the trace here. You don't need that jumper. And that's the other current shunt resistor right here. That's a very low value. And you can see that that goes out to the two collectors where the current goes into that transistor. So yeah, pretty simple driver. Let's get into the TEC controller. To control the TECs on the inside of the laser head, I'm going to use a very simple circuit based on the LM393 comparator IC. And to explain how the circuit works, let's go ahead and start with that part. So here's the LM393, and it's actually a dual comparator, which means that it has two comparators built into one package, and they share the same input as far as power. So to power this chip, you have a negative input, and you have a positive input. That leaves us with 3 pins per each comparator. Now I only have one of them wired up in this diagram, but I can go over what those functions of the pins are. Here with this red dot is our positive input, which is also known as the non-inverting input. This one with the black dot right here is the inverting input, and then we have the output here. And to turn on the output, what we need to do is we need to have a higher voltage on the negative input in the positive than we do on the positive input. So for example, if we have 5 volts here and 3 volts here positive, the chip will turn on. Now when it turns on, what it effectively does is it makes a connection between the negative input over to here. So if you had an LED with its negative connected to the output of the comparator and the positive connected to the positive rail here, when the voltage was higher on the negative input, the LED would light up because it would make that connection. I'm using that negative output to control this P-channel MOSFET. Now, there's an enhanced mode MOSFET, and to keep it off, I'm using a pull-up from the positive rail, and that ensures that the MOSFET is off until it receives a negative pull-down signal from the comparator. When the P-channel MOSFET turns on, it conducts the positive from the positive rail up through and to the gate of this larger N-channel MOSFET. And there is a pull-down resistor between the gate and the source just to ensure that this MOSFET is off without that positive signal. So how do we control what this is doing? Well, let's start off with our divider circuit for setting the temperature. That is done with a potentiometer right here, and that forms a divider between the positive input and the negative input, and we can control what voltage is on this connection by turning the sweeper. So if we set the sweeper closer to the negative input, the voltage will be lower, and if we move the sweeper closer to the positive, then the voltage on the sweeper will be higher. Now, I'm running this at about 5 volts, so I'm using a 10K potentiometer, which works fine. If you're going to use higher than 5 volts, you might want to jump to a 20K, so that way the potentiometer doesn't warm up and drift at all. The sweeper of the potentiometer comes up through here and connects up to these 2 pins. And this is actually a grouping of 6 pins right here. These 2 middle pins connect to the positive and negative inputs of the comparator down here. So what I can effectively do is control which input on the comparator I send my voltage reference to. So for example, if I wanted to send it to the non-inverting positive side, I would put a jumper between this pin, and that would send the signal up through here and into that input. Same thing on this side. If I connect this pin and this pin together, then the signal is passed through the inverting input. So how does the thermistor tie into all of this? Well, we have these 2 pins here and this section up here. So the thermistor actually goes on these 2 pins, and it's like a resistor that changes with temperature. This is the negative side, and then we go here and over to here. So I'm using a 10K, and that gets connected to positive, which means that we have another voltage divider between the negative and the positive. The voltage will change at this point between the thermistor and the resistor as the resistance value changes on the thermistor. Of course, we can direct where that goes. So, for example, we can connect these two pins together and that would send a signal from the thermistor down this way. Or if we connected these two together, we could send a signal from the thermistor down this way. So we can configure what we want this driver to do based on how we calibrate the connections in the circuit. And so let us use PTC or NTC thermistors and even set this so it can heat or cool. Now the circuit does not have any constant current control, nor is it an H-bridge, so it's very limited. It can only control whether the TEC is only doing warming or only doing cooling. It cannot do both because there's no way to flip the polarity with this circuit. So there is a limitation. Let's go ahead and take a look at what the board looks like. Now keep in mind that I'm using both of the comparators because I have two TECs that I have to drive. But you can see all the components that I talked about on the diagram. We have our two comparators. These are the pins for the thermistor inputs. These are the 6 pins that allow me to select the function of the comparator, such as PTC or NTC thermistors, heating and cooling. These are voltage dividing potentiometers that allow me to set the voltage reference, which will let me calibrate the temperature set point. Some indicator LEDs. On the other side, I have my 2 P-channel MOSFETs, and they have their associated pull-up resistors, and then my final larger N-channel MOSFETs up here on the heatsink, and their pull-down resistors. So, yeah, about the only thing I don't have drawn on the diagram is the capacitors that go between the positive and negative here for smoothing of any kind of ripple that might be coming from your power supply, which is these 2 electrolytics here, and then these 2 thin film plastic caps there. But here's what that board looks like. And if you're making boards like this yourself, whether it's the laser driver or the TEC controller, you're sensing very little voltages. So you don't want any kind of residue conducting any kind of noise or stray signal from any of the other electrical connections. So it helps it perform better. But yeah, so hopefully this is all I need to drive one of these laser heads. At this point, I hope you have a decent understanding of what's inside of the laser head and the circuits that I'm going to use to try to drive those various components, because this is where it all comes together. Alright, so I'm going to start off with the thermoelectric cooler side of things. So let's think about this logically real quick. The pump laser diode likes to run at about 33 to 34 degrees Celsius, and the resonator likes to run around 30 degrees Celsius. So the resonator needs to be cooler than the pump laser diode, which means that we're going to be taking the heat from that component and putting it over to the copper block that houses the pump laser diode. Now the pump laser diode generates heat too, so that's 2 sources of heat that is on that copper block, which means that we need to also cool down that component. Now if it was a very, very, very cold environment, sure, we may need to actually heat the pump laser diode, but not in this case. So I think using the cooling portion of the TECs is going to be the best option. So that's how I'm going to configure it. I'm going to configure the resonator TEC to run cooler than the pump, and I'm going to set the pump laser diode TEC to run cooler than the base, and then we'll just go ahead and dissipate any of that thermal energy through this cooler here. So let's start with hooking up the thermistors. I'm going to start with the pump laser diode thermistor, and I have my wiring diagram right here. So this board has shared ground connections between the 2 thermistor inputs, and I have labeled that with a little black marker on the side here. And I've also done the same with these wires here. So see, that's black on that side and black on here. Now, since we have a common between those 2 thermistors, I'm only going to be using one of the negative grounded connections, and the other one will just simply float freely in the breeze. So let's go ahead and plug that on there. The black one is going to plug to thermistor common, which is, I believe, that one, according to my wiring diagram. And then this one I'm going to plug into the pump diode thermistor wire that I have on there after that modification. Okay, so that's the first of the two connections. Now on this driver board, I have a little LED here, and I don't have the TEC connected at all to the output. What I want to do is I want to find the set point where it's at about room temperature, because I don't want to connect this thing up and have it get hot or cold and not know where my temperature is right away. So let's go ahead and find that ambient temperature set point, which is really easy. I'll just be turning this potentiometer right here. I'm going to turn off the light so that way you can see the LED. Turn on the power supply, give it 5 volts. All right. Now I want to turn this to the point where the LED just kind of is in between the on and off state. So let's find that. Alright, so about right there is that set point. Turn off my 5 volt power supply. And then I'm going to connect the other thermistor up. So make sure that that is in the correct polarity with that black on that black. And then I'm going to connect the other one that isn't marked onto the Xtel thermistor wire that I have right there. So now both thermistors should be successfully connected. So same thing, I'm going to find the current ambient temperature set point, which will be when that LED is kind of in the middle of going on and off. Same thing, but I'm going to be tuning this potentiometer here for that. Okay, it's check my connections time. Got that ground wire connected. That explains a lot. Let's try this again. Once more with feeling. Okay. That should be both of them set to where I need to have them calibrated. Now, I'm going to connect the actual TEC power wires. And I already have it labeled here, which is negative and which is positive. So, do that. Let's see, we're going to hook up the pump diode laser one first, which is this one, and it is the outside wires. Okay, so like that and like that. Now I will tell you, if you're using this circuit, you might want to also use like a 1 ohm or 2 ohm resistor in series for very small TECs, like for resonators and stuff like that. It'll help cut down the thermal oscillations and stuff. Alright, and then the next one we're going to plug in is the crystal TEC, which is the second to last outer pins. Like that. So that should be both TECs now connected up. And the last thing to do then, really before you start calibrating, is connect up the pump laser diode driver. So I am going to set the current to 1.5 amps. Same thing as I did before. Here's my meter. And I'm going to configure it for doing the amps in DC. Let's see, I need to connect the anode up to okay. That's the anode. Now I'm going to connect my meter in series with everything, so that gets connected in series with the cathode. So that's should be that. I'm using this pin and this pin right now. And then I'm going to connect the common of the meter to the negative of my driver. Driver gets connected to 5 volts in this situation. As Riddick says, looks clear. So, yeah, let's calibrate the current then. Turn on everything. Very good. And I'm going to raise this up so it says 1.5. Alright, and this was the laser head that was only doing about 2 milliwatts. Let's see if we get any output. Get a little bit of green light, but not much. Alright, at this point, we have to play around with the TEC temperatures, I suppose. Kind of want to calibrate that up to a higher current, though. And we'll give it another 100 milliamps. Well, that's actually calibrated at this point, so you can go ahead and remove that from being in circuit, so that we can get rid of one more thing. Alright, let's see if we can get anything noteworthy from this laser. Now, here's my laser power meter. In order for anything to show up on here, we need at least 10 milliwatts, because right here is the 1/100th of an amp, here's the 10s of an amp, and then the 1s is just not there. So, that's the resolution I'm dealing with right now. Let's see if we can get some power out of this. Probably gonna have to wait till the laser warms up on its own before you set the TECs. This could take a while. Alright, I'm going to start setting the temperature set points on here higher than ambient room temperature, so that way everything can come up to its proper temperature. So I've been playing around with this for about the last 2.5 hours, and I'm very close to the temperature set point. Now mind you, this is the laser head that had the high hours. I was only putting about 2.9 or so milliwatts out. I'm going to point out something real quick. So here's our output, and it gets brighter and dimmer, and that's because of the thermal oscillations because of the TEC controller. Now the original laser head had constant current control, and that what it did is it allowed the driver to control how much current was going to the TEC. So thermal oscillations happen because when the TEC turns on, it cools down the part too cold on the inside of the laser head, so it overshoots, gets too cold. And that's because there's a small delay from the area where the TEC is that gets cold and the temperature sensor. So you're overcooling to the point where that reading gets to the temperature sensor. By that point, it's too late. Kind of like you're kicking it too hard and it's overshooting. So we're actually getting quite a bit of power. I'd say maybe 10 milliwatts when it's at that right temperature point. And it doesn't take much. Only a degree, a fraction of a degree, and that can change your output power drastically. Now, one of the things that I can do to solve this is try to add a resistor in series with the TEC, so that way I'm limiting the amount of current that's going to that that TEC, and so I can prevent a little bit of that overswing, that overshoot, hopefully knock down some of that thermal oscillating from happening. Let's go ahead and see how effective resistors are as far as eliminating that thermal oscillation issue. So I have a resistor here. You can't see it very well, but it's in series with the pump laser diode TEC, and it's 1 ohms. And here I have 2 resistors totaling about 17 ohms in series with the TEC for the resonator on the inside of the laser head. Now, the reason why I have 2 different values is because I have 2 different masses. I have that larger mass that the pump laser diode is in, and I have that smaller mass that the copper black and crystal comprise. So, I'm going to go ahead and turn off the light. Let me take a look at the output here. And if you notice, the output is no longer oscillating. It is rock solid. Take a look at the TEC controller here. We can take a look at this LED, which shows activity on the resonator, and it's holding rock solid. So the resistors are really effective as far as ballasting the extra current that you don't need and stabilizing that temperature out really nicely. Now, there is a downside to using resistors like this, and that is that you narrow the operational temperatures that you can run your laser in. So, for example, if the environment is too cold, it would not have enough power to warm up the crystal to the right temperature, and vice versa. If it was too warm, you wouldn't have enough electrical current going in to actually cool it to the right temperature. So right now the biggest stabilizing factor is the temperature of the pump laser diode. As long as we can keep that section pretty stable, we shouldn't need much energy to keep the stability of the resonator. So yeah, it's amazing what you can do with rudimentary electronics if you have an idea of what's going on. So, works good. I'm very tempted to modify the other laser head and see how much output power that can do. As I said, this was the laser head that was only doing about 2.9 milliwatts. Look at this, we have a pleasant surprise. So I went ahead and did that modification on the other laser head. We're already seeing improvements. Look at that, 40 milliwatts. Stable on simple analog electronics. Can't believe it. This is why I have trust issues in digital stuff. That's pretty nice. Well, I didn't manage to beat 40 milliwatts, but in the end I got the high score, and 40 milliwatts is not bad for a laser that was stabbed and blowtorched. So, we'll give it a little bit of credit. But I'll tell ya, the speckle on this laser is amazing. It is a very narrow bandwidth laser. Take a look at the output on here. Yeah, that is amazing. I just can't get enough of good speckle. How about some fog? See, we get the hyperspace lines. Oh, yep, there they go. Yeah, that's a decently nice laser. Maybe one day I can get full power out of it, but for now I think that's where I'm going to wrap up this project. Here are some of my final thoughts regarding the LasNova 50. First of all, if you're just getting into fixing your own lasers, I can't recommend this one to you. The two main things that fail in a DPSS laser like this are either the TECs, in which case these are almost impossible to remove, and secondly, the pump laser diode, which if that fails, you need to replace it, which is normally easy, but the problem is they need to be temperature calibrated so they produce 808 nanometer laser light most effectively, and since you can't set the temperature in the program, it seems, there's no way to adjust that. However, if you get one of these lasers, they have an incredibly narrow bandwidth. You can see by the beam, there's quite a lot of sparkle to it, and they're very round circular, very Gaussian beams, so probably really good for holography. I'm going to show you a little demonstration of how narrow the bandwidth is. So I've got this piece of perforated plastic. You can see there's little holes in it. Zoom. There you go. Well, that's difficult with the laser, isn't it? Okay. There you go. It has these little holes. And I also have this piece of old speaker grill from a laptop. So things with repeating patterns. I'm going to turn off the shop light. And I have the laser shooting this way to the other side of the shop room here and back on this piece of white material. Step over here. I'm going to put the speaker grill from the laptop in the beam first, and we'll see some neat interference patterns. And next, I'm going to put this piece of perforated plastic into the beam. And even things like my arm hair can get some pretty good patterns too. And that is just... So there's my arm in the beam. So if you think this is cool, go ahead and try this out at home. All you need is a DPSS laser. A 532 nanometer laser should work just fine. You need a mirror placed on the other side, a distance away. You shoot the beam in the center of the mirror, and then what reflects back towards the laser gets these neat diffraction patterns. You can see the square though, and that's actually due to the mirror on the other side of the room. That is so wild. Later on this summer, I'll be making a video about the Protera lasers manufactured by Novolux, which have a reputation for being some of the most unstable lasers ever manufactured, but they're also very narrow bandwidth. So as always, stay tuned for more.